All right, today I'm going to walk you through the laws of thermodynamics. I wanted to use a PowerPoint because there's some pictures that I want to share along the way, and I think I'd like to be able to say a few words and help explain a few things versus just doing a static PowerPoint. So let's see how this works. All right, first of all, there are 4 laws of thermodynamics, and they're numbered kind of weird. They're numbered the 0th, the 1st, 2nd, and 3rd law of thermodynamics. And this is because they had already discovered and named the 1st law when they realized that they had to go back and clarify something. So instead of renumbering them, they just inserted a 0th law. And also, unlike Newton's laws of motion, the laws of thermodynamics are stated in a variety of different ways. If you called somebody and said, "I forgot Newton's 3rd law of motion, can you tell me what it is?" They very quickly say, for every action, there's an equal and opposite reaction. Well, you're going to see that the 4 laws of thermodynamics are not so clearly stated. Lots of different statements, lots of different implications, and so you just kind of have to pick the statement that resonates the best or the most with you. Einstein also made this statement at one time. I won't read the whole thing, but it says a theory is the more impressive, the greater its simplicity, the more different kinds of things it relates to, and the more extended in its area of applicability. So, in casual language, I think he means that the simpler the idea, the more different things it can relate to, the more applicable it is more likely to be a true law that will never be overthrown. Think of F equals ma. It was simple, but it related to a lot of different things. We applied it to a lot of different things, like I'll say a box, going down an inclined plane, all the way to showing how an hot air balloon can float in the air, or my boat can float on water, etc., etc. And Einstein is saying that he thinks the laws of thermodynamics also have this feat. Okay, we're going to start with the idea of a temperature scale. And so temperature scales are generally based on the freezing or boiling point of water or absolute zero. So on the left here are what I would call the SI or the metric units of temperature, and on the right will be our English or imperial units of temperature. So you already know about Celsius and you know about Kelvin, but you can see that Celsius is based on the freezing point and boiling point of water, 0 and 100. So is Fahrenheit, but our numbers just aren't as pretty, 32 degrees and 212 degrees. But other people thought that it was more helpful to start 0 down at absolute 0 where all motion stops. And so we see that if I want to do Kelvin temperatures, like we're going to have to do in this unit, I'm going to have to add 273 to all of my Celsius numbers. But you may not know this, that we also have a temperature scale that starts at absolute 0, and that's called the Rankine scale. I should have spelled that word out. It's Rankine, Rankine. So when you have to do some temperature conversions, use your calculator conversion menu, and you'll find a K, C, F, and an R in that menu. At least you should. All right. Also, last time I was going to California, I took a picture of Flight Tracker. I love Flight Tracker. And so Flight Tracker tells you all of the measurements that are going on around you or in the airplane. And you can see that at this particular moment, we were at an altitude of 9,000 some meters. The outside temperature was negative 46 Celsius. That's pretty cold, pretty cold. And you can see we were actually traveling at a ground speed that would take into account the airplane's speed, the pilot's speed, and the wind speed. We had a ground speed of 776 kilometers per hour, which I converted for you. That was 482 miles per hour at that moment. But you're going to need this picture to do homework, for your homework number 2, just so you know it's in the PowerPoint. All right, the next thing, we are going to introduce today the concept of internal energy a little bit more formal. So we've already talked about temperature, which is going to be the variable T. We've already said that heat is going to be a Q. Internal energy is a U. The energy associated with the random, disordered motion of molecules. So if we have something that's moving, usually people call that kinetic energy. But if we're talking about molecules that are not necessarily moving from point A to point B, they're just like vibrating in their place, or they're just bouncing around, that is not kinetic energy. That's considered internal energy. And the equation for internal energy is 3/2 nRT. Or sometimes we talk about the change in internal energy. And if I'm measuring the change in internal energy, it would depend on the change that's happening in the temperature. So because things are very complex in terms of the motion of molecules, we down here often limit our discussion to ideal gases when we talk about internal energy. So because we're talking about an ideal gas, we need to know how much of it we have. And so N is going to be the number of moles. R then is going to be the universal gas constant, which you learned in chemistry, but you probably learned it with a different number because chemistry people use different units. In our units of joules divided by moles degree Kelvin, it's 8.314. And then the temperature, when we talked about heat, you were able to leave things in Celsius. We now have to have things in Kelvin. So again, if you're given a Celsius temperature, add 273. We should also know that internal energy is the lowest form of energy. And that means it is the least useful form to harness in terms of doing work to help us in our everyday life. Electrical energy, that's useful to me. I can plug something in and I can make toast. But if you just give me a can of gas that has bouncing molecules, I can't make toast with that. So internal energy is a form of energy, but it's a very, very low, almost useless form of energy to us at this time. All right, so let's start with the zeroth law of thermodynamics. You might think it's kind of simplistic, but its analogy is Newton's first law of motion. Newton's first law says, an object at rest will remain at rest. And that wasn't very exciting, but it defined that something has to be happening in order for that object to move. All right, so it could go something like this, and I'm going to click out of my PowerPoint here for a second. So it says if object A is in thermal equilibrium with B, so I'm going to make it touch like this. So they're in thermal equilibrium. And if they're at the same temperature of thermal equilibrium, it means that there's no heat flowing between them. And if B then is in thermal equilibrium with C, meaning there's no heat flowing between these two, then we can imply that if I brought these two together, there'd be no heat flowing between those two objects. So that seems kind of silly, but that's what the first statement says. So it's this idea of, in math class, I'd call it the transitive property. A to B, A to C, therefore B is related to C. Or we could say it a different way. If two substances have the same temperature, they are in thermal equilibrium. Heat will only flow as a result of a temperature difference. Or if two substances are at the same temperature, then no heat will flow. So they're all saying the same thing. You can pick any statement that you like. I kind of like the last one, that's why I made it red. So an object at rest remains at rest. If two substances are at the same temperature, then no heat will flow. All right, moving on. So now we're going to look at James Prescott Joule. We've been talking about Joule for a long time, But now this is his claim to fame. He designed an experiment that demonstrated something that's now called the mechanical equivalent of heat. So it says his famous experiment consisted of a closed container, that's this box, that was filled with water, and then it had a thermometer in it. And then there was this paddle wheel. A paddle wheel is like just something that can go around and spin, that was attached to a pulley system. And then over here there's a weight. So this weight isn't doing anything right now because it's sitting on this block, which they called a constraint. So then Joule took away the constraint. So he took away the constraint, so you can tell that the weight's going to fall, and when the block falls, then the pulley's going to turn. That's going to turn the paddle wheel, and as the paddle wheel turned, the temperature increased. Now, maybe that seems intuitive to you, but back in Joule's time, that was not intuitive. So it's like, oh my God, a falling weight. So a falling weight is doing work. And work is a form of energy. And so a falling weight, like when I say work, I mean F times D. So a falling weight, FD, FW, times the height that or distance that it falls, increased the temperature of the water. So a falling weight created heat. So Joule concluded that heat must be a form of energy. The more work that happened when the weight fell, the more heat that I got. And so people did not think that heat was a form of energy back then. So that was like a big, big deal. And I told you at the beginning of the school year that physics is divided into 5 topic areas. The first topic area is mechanics, which has work and energy in it. And the second topic area is heat and thermodynamics. So Joule now tied together the concept, the big grand concept of mechanics, to the second big grand concept of heat and thermodynamics. So he just made a connection between 2 out of the 5 main topic areas in physics. And again, that's one of the things that we're going to see in all 5 of the topic areas. This concept of energy flows through all of them, and we're looking for ways to tie that together. So this was a big, big deal. It is for this reason that we have decided to name the unit of energy after Joule. It was after this experiment. All right, so moving on then, taking what Joule just discovered brought us to the first law of thermodynamics. So lots of different ways to say it, but both heat and work are forms of energy. In terms of conservation of energy, heat can be considered a form of energy. Energy is always conserved. That would mean that the heat lost by something would be equal to the heat gained by something. I'm going to pause here, because if we were at school, we would do a cool lab now. So the cool lab is over here. That's this picture that is showing. So you take a little cork, and then you take like a pin or a needle, and you put a piece of food on it. So in this example, it's showing a peanut, and we actually use peanuts in class too. So you know that food has calories, but calories can be converted to joules. So there's joules in this food. And so we would take the joules in the food, that would be the heat lost by the food, and turn it into the heat gained by the water. So we're going to burn the food. We literally light the food on fire, and the flame from the burning food heats the water. So if something has a lot of calories in it, like peanuts actually have a lot of calories in it, and so we get a pretty good increase in temperature of the water here. Then we try to burn something else that doesn't have as many calories. I'm trying to think of something. Rice. How about a piece of a rice cake? Rice cakes don't have many calories, and we don't get as much increase in temperature of the water. It's a really fun lab to do, but honestly, we get really, really bad results. And we get really, really bad results because all the heat lost by the food is not necessarily gained by the water. It's lost to the surrounding air. We lose too much of the heat.